Hey guys, it's Chili here. Welcome back to RPG Project Twin. Today's episode is a little different. I'm going to be going more in depth than usual on the concept of alpha blending, how it is accomplished, and then we're going to take it even deeper, and I'm going to walk you guys through the process of optimizing the function to make it real fast. So there's going to be lots of detail in this video. Let's get started. Alright, so now we can load PNG files, we can load stuff with an alpha channel. What is the point of this? So that we can draw with alpha blending. And so your next question is, well, what the fuck is alpha blending, Chili? Well, let me show you what alpha blending is. So we're drawing our game screen, and on top of this, we're going to draw this image. Now watch what happens when I walk underneath the dice. You see what's going on here? Chili is shining through the dice image, and basically what's happening is they're being blended together. So the image of the dice is being drawn over top of the pixels underneath and is being blended with those pixels. That's alpha blending, and that is the thing that we are going to be achieving. Now if we look into spriteeffect.h, you can see here is the alpha blend effect, and it's a little bit of math here, nothing too complicated, but let me give you a very quick rundown of how it works. Now the way that alpha blending works is you're drawing one pixel over top of another pixel, and the pixel that's underneath, the idea is that it shines through. So you're actually blending the colors of the two pixels, the old pixel, that color that was underneath, and the new color that you're drawing over top. Now that blending is achieved by a more general concept called linear interpolation. So let's explain that. Let's say you've got two values A and B, and you want to find a value that is halfway between them. Well, we know if we want to find something that's halfway between two values, we just average them. We add them together, we divide by 2. Now you can rewrite that as A divided by 2 plus B divided by 2. And you can rewrite that as 0.5A plus 0.5B. And this is the way we like to think about it. So we can call these values here weights. And you're weighting A and you're weighting B, and you're giving them equal weight so that they both contribute equally to the final value. Now let's say we want to take 75% B and only 25% A. How do we do that? Well, we just go 0.25 times A plus 0.75 times B, and we can control how much of A we take and how much of B we take by changing these values. Now these two values have to add up to 1, otherwise we're going to be losing value, we're going to be attenuating, or if they add up to greater than 1, we're going to be amplifying. So if these two weights have to add up to 1, we can rewrite this in a way that only uses a single parameter. So we'll let alpha mean the amount of A that we're going to take. So alpha times A, and the remaining amount, because they have to add up to 1, so the remaining amount is just going to be 1 minus alpha, and that is how much you take of B. And this is the concept of linear interpolation. Alpha is the controller that controls how much you take of A, and how much you take of B is just whatever remains. So when we do alpha blending for two pixels, all we do is we do linear interpolation, and the alpha value that controls how much of the source and how much of the destination you take is the alpha channel in the source, or in the sprite that you're drawing. And this is dependent upon per pixel. So some of the parts of the sprite can be very see-through, and other parts can be completely opaque. Now, one last issue is that our alpha channel and our color channels, they're all byte values. They range from 0 to 255. They're not floating points from 0 to 1. So the way we do this, we could convert them to floating point 0 to 1 and then convert back, but that's slow and that's dumb. So what we do instead is, instead of doing alpha times A plus 1 minus alpha times B, we do alpha divided by 255 times A plus 255 minus alpha over 255 times B. And alpha ranges now from 0 to 255, so this ratio here is going to range from 0 to 1 when you do the actual division. And this can be simplified to alpha times A plus 255 minus alpha times B divided by 255. And this is equivalent, but this does it all in integer math. You don't have to go into the floating point domain. And that's what this code is doing here. It's getting the destination pixel for the blending, it's extracting the alpha from the source, it's getting the complement, which is 255 minus alpha, and then here we do source times alpha plus destination times complement divided by 256, and that's for the red. We do the same for the green, same for the blue. Now you might be saying, Chili, you said divide by 255, here you're dividing by 256. Well, Basically, dividing by 255 is very slow, but if we divide by 256, that is a power of 2, and what the compiler will do is that will replace it with a bit shift, right bit shift, which is incredibly fast. So we're changing the divisor by a little bit. We're going to have an error factor of about 0.4%. That will not be perceptible to your human eyes, and it will make it a hell of a lot faster. So it's a great little simplification there. And then after you have calculated the blended values, the linear interpolated values for RGB, then you pack them back up into a single color value with the constructor of color, and you put that onto the graphics surface. And that, my friends, is the basic idea of alpha blending. Now, I know in our engine that the bottleneck here is going to be the graphics rendering, the software graphics rendering of the sprites. And alpha blending in particular is going to be very slow because you've got to read from both the source and the destination, and you've got to blend them together. So what I want to do is I want to make it as fast as possible. And the first step to doing that is to make sure you're actually measuring your performance before you start making optimizations. So up in here, I removed the benchmarking code from the update because that's not really important. We've established the update is not going to be very big of an issue for us. I create a bench timer here, and then I mark the time down here, and I output that to the debug console. So every frame, we're going to draw our test sprite, the dice, which is a very big sprite, and it'll be a decent test with the alpha blend sprite effect, and then we check the time. And when I check the time, I found that in general, it takes me about 2.4 milliseconds to draw that sprite. Now comes the optimizations. And the first optimization what I did was I realized, and this is a very common optimization, when we do the alpha blend, we unpack the RGB for the source, we unpack the RGB for the destination, and we multiply them by alpha and by constant alpha. But every time for the sprite, this R times alpha, this G times alpha, it's never going to change, right? The G and the RGB are the same for every pixel in the sprite. The RGB for any given pixel in a sprite never changes, and the alpha of that pixel never changes. So what we can actually do is we can, when we load that sprite, we can pre-multiply this R times this alpha, this G times this alpha, and store it as a pre-alpha multiplied pixels. So we'll call this pre-multiplied sprite, we'll call it a baked sprite. So if we bake our sprites when we load them once, then when we're doing the drawing, all we have to do is do the multiplication for the destination. We unpack the channels of the destination because we don't know that ahead of time. That changes every frame, right? So we unpack the destination, we do the multiply by the complement of alpha. And then all we have to do is add together the pre-multiplied. This is doing the multiplication and the division by 256, by the way. And once we've done that, all we have to do is add together the 32-bit values that have all the packed channels. We can add them together here. And the reason why we can add them together like this, we don't have to add them as individual channels, is because we've already divided by 256. So the individual channels, when we add them together, once we've pre-multiplied and scaled all of the channels, this is going to be the R, G, and the B channels here in these packed 32-bit values. When we add these guys together, none of their results will be greater than 255 in any of these columns here. So none of the results will flow over into the other channels, and we don't have any problem. We can add them together as packed 32-bit values, as long as we pre-scale them before we add. And this gave us only a tiny bit of improvement. It went from 2.4 milliseconds to 2.2 milliseconds, which is less than I hoped for, but we still got much more to explore here. Now, what I've done in my second change here, instead of packing using the constructor for color and then adding together the D word values, what I did here is I packed with bit shifting. So I shifted the red channel and the green channel into its proper position, and then I added together all these channel values with the packed D word of the source. And this gave me slightly better results. I basically got it down to 2.0 milliseconds now. So we've started at 2.4, we're now at 2.0. The next change is going to be huge. And this change is, it's a tricky one to understand. So let's say I've got some 32-bit color value, A, R, G, B. Each one of these letters represents a nibble or four bits in there. And what I'm doing is first of all, I want to mask out the A and the G. So we isolate R and B in their places. Now, if I multiply R and B by the alpha value, the result here is going to be some kind of multiplicand of R, right? The maximum you could get out of this 2 nibble by 2 nibble multiplication is 4 nibbles, and the maximum of this 2 nibble by 2 nibble is 4 nibbles. So these multiplications here, they won't affect each other because they have the buffer spaces of these zeros. And once we have that, now all we need to do to divide by 256 is we shift right by 8 bits. So shifting right by 8 bits kills this guy. And now all we want to do is mask this guy out with a bitwise and the result is the multiplied and scaled red and blue. And we did it all without having to unpack them individually. And that's what we're doing here. We're masking out the green. We do the multiply by the 8-bit value, we shift right by 8, and then we mask again. And we do the same thing only for the green value here that was left, and then we can add together the red-blue packed plus the green plus the packed values of the source that have been pre-multiplied. This gives us a huge speed up, 2.0 milliseconds to 1.4 milliseconds. Now the next improvement we make is pretty simple and it is enormous. So what we're doing here is, well, we calculate the alpha complement, right? That's just 255 minus the alpha. Now if the alpha complement is equal to 255, that means that the alpha must have been 0. So what we're doing here is we're basically checking to see if alpha is equal to 0. Because if alpha is equal to 0, that means we're not going to draw shit, we're going to leave it the way it is. And so we skip the whole blending process and we just don't draw a pixel. So this early rejection of pixels that have an alpha value of 0, basically completely invisible pixels, gives us a huge speed up, which you might expect. So we go from 1.4 milliseconds down to 0.79 milliseconds. And this is where I say, you know what? This is good. This is good. We basically tripled the speed of our alpha blending routine. We did a good thing today, and we can pat ourselves on the back. Now, there's one thing I missed when I was doing my explanation here. When I explained pre-multiplying, I said we had to bake the sprites, but I didn't show you the function for that, and that's just right in here in Surface. I don't optimize it or anything. It's a very simple bake alpha, and it just multiplies, it extracts the alpha channel, then it multiplies RGB by alpha, divide by 256, write it back. So this is the pre-multiplication. You have to bake any sprites that are going to be drawn with alpha. And then after we do all of this optimization bullshit, what I do is I want to enable basically dynamic choice in the codecs when we load a surface of whether the surface gets baked or not. So what I did in here is I checked to see whether the file name path, whether it contains PM underscore, which stands for pre-multiply. And if it contains that string, then after we've loaded, we also call bake alpha on the surface. So whether or not a sprite requires pre-multiplication is going to be determined by its file name. PM underscore means it'll be pre-multiplied. And that's basically it. Now we have super fast drawing of alpha blending. I did the test on this, and basically with alpha effect enabled, we can push about 500 million pixels per second, which is way more than we're going to need for this game. So we've got the performance game on lock now, and it looks pretty fucking sweet here. And more important than just the special effect of being able to see through shit is it's going to enable us to have sprites that have smooth edges that are blended into the background of our game, and you'll see that later on, especially when I create the first test boss. Anyways, just to wind out this episode, we did a couple of cleanup things in the code. I used mem function instead of bind. And the last thing I did here was just remove the test code for the alpha blending, remove the drawing of the alpha dice. And that's gonna about do it for today. Let me know what you guys think about, a video like this with a lot more detail. Because, obviously, more detail is great, but this actually slows down the progress of Project Twin a lot. So if you guys don't really want it that much, let me know, and I can speed up the progress of the game. Either way, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, it helps a lot. And I will see you soon with some more Project Twin.